Hello, my Algebra 2 students. It is day 4, which means we are doing modeling with quadratic functions. There's a lot of stuff that we are going to be doing with this, but you definitely need your calculator. So if your calculator isn't next to you, please go get it. Right? So starting with this, we're just going to run through a bunch of different examples kind of showing how you can model different situations with parabolas and then how to solve for the different things that you might need from there. So the first one, it's saying an object is fired upwards with an initial velocity of 112 feet per second. Its height in the feet above the ground as a function of time in seconds since it was fired is given by this equation. All right. So sometimes we're going to have to build equations. Sometimes they just hand us the equation. So there's the equation we're working with. As always with word problems, I think it's smart to figure out what do H and T represent. So for this one, they're saying T is talking about time in seconds. H is representing the height. And what's also good to note, T is acting like the X, H is acting like the Y. All right, so just set those things out to start from the beginning. So when it says, at what height was the object fired from? All right, well, when the object is fired, that's the start time. All right, so that's at time equaling 0, which this is the same as x equaling 0. They want us to then find h, right? And so if we want to find h at x equals 0, well, then all we have to do is plug in x, or I should say t equaling 0. So if we do h of 0 equals negative 16 times 0 squared, and then plus 112 times 0. You guys don't need a calculator. You can see that that's going to go right to 0. So when the object is fired, it's starting on the ground is basically what you're seeing here, because the height is 0 feet. And so that's how you'd actually interpret that. All right. Part B, sketch a general curve of the equation. Okay, well, the idea is it's starting on the ground and they're launching it up and then it's coming back down. Right? Could we use our calculator to help us with this? Of course, but you can tell by the fact that it's a negative x squared that it's going to be an upside down parabola right off the bat. If you would like, we can grab our calculator here. If there's anything in there, get rid of it. Let me darken this up a little bit so you guys can see it better. And so then we could type in negative 16 x squared and then plus 112 x. Because remember, x is starting the same thing as t. And then if I zoom 6 it, I'm not going to see necessarily all of it, but I can see some of it. All right. So I can see that it's starting at 0. It's coming back down. Right, at 1, 2, 3, 4, 5, 6, 7. So by 7 over here. Right, and then it's opening up and doing something like this. Right. So we'll get more specific in a moment. All right, the next part says, algebraically find the time that the rocket reaches the greatest height and the maximum height itself. So we want to know what time it reaches that height and then the actual height of the rocket. So we want the x and the y, right, of that top position, which is code for this guy right up here, all right? So we want to actually find the vertex. Now, to do it algebraically, there's 2 ways. We could go through and we could complete the square. That's one way to do it. The other way was that little shortcut that was in the notes from yesterday, and that was by calculating the axis of symmetry, that negative b over 2a. Right? So if we do that, looking at your equation, the a is negative 16, the b is 112. If we calculate that x will be equal to negative b over 2 times a, that will come out, if we get out of here, negative 112 divided by 2 times negative 16, 3.5 right there. So that's the x coordinate, right? So over on our graph, that kind of makes sense because we could just see that it was hitting at 7 and we knew it went up from there. So at 3.5 is where it's going to hit this maximum spot right here. And then if we plug that back in, so if we plug in negative 16 and then times 3.5 squared plus 112 times 3.5, that would definitely be some calculator work. If you trust my calculations, it comes out as 196. So what that ultimately means is at 3.5 seconds, it reaches a height of 196 feet. All right. So on my graph, I can come on over here and I know that that's at 196. That's the coordinates of that point right there. Now, if it had said just do it graphically, then we could calculate the maximum point. That would be kind of your backup way to do it. But algebraically, that's how we can show our work. Find the axis of symmetry and then plug that value in. And then that'll give us the actual coordinates of the vertex. All right, last piece of it. It says algebraically determine the time when the rocket reaches the ground. Okay, well, we kind of saw that when we were graphing it. So it goes up, comes back down, and we could literally count the tick marks to see that it was hitting the ground at 7 seconds. But if we play along really quick, if we talk about algebraically determine when it reaches the ground means it has a height of 0. So you're essentially setting h or y equal to 0. So if I take that equation and I put 0 in on the left, I would have negative 16t squared plus 112t. And then we've talked about how to solve quadratics. First thing we should look for is a GCF. So when we take out a GCF, I would probably take out negative 16. Positive 16 would be fine too, but I'm just going to take the negative right out. And then t as well. This would leave me with t here. If we do 112 divided by, negative 16, that comes out to be negative 7 right there. And you can kind of see where that 7 comes in. So this piece of it, when you set it equal to 0, just ends up producing the t equaling 0. So there's that x-intercept. And then this piece of it, the t minus 7 equals 0, that produces the other one. And so at 7 seconds is when the rocket will come back down and hit the ground there. All right, let's keep on moving. We're going to jump right over example 2, and we're going to go to example 3. We may or may not come back and talk about example 2 in class. All right, example 3 has a lot of parts. It's talking about the Crazy Caramel Corn Company, hard to say, has determined that a percentage of kernels that pop rises and falls with the temperature of the oil that the kernels are cooked in. And it's saying it models this trend using the equation. All right, so don't worry about how they got the equation. Just take it, say thank you very much, and keep rolling with it. But the idea behind it, think about if you're popping, popcorn, even in the microwave, that initially you're not, there's nothing. And then it starts to pop a little bit and then a ton. And then if it gets too hot, then everything kind of like burns up. So you can see that the number of kernels pops increases and then it starts to decrease. So right here, you can see how this is going to fit a quadratic shape. So when it's saying P represents the percent of the kernels that pop, awesome. And then T represents the temperature of the oil. So feel free to write over here, P is like the Y value. That's the percent of kernels that pop. And then T, that is like the X value. That's the temperature of the oil. I still think it's helpful to kind of write that down. All right. Algebraically, determine the temperature at which the highest percentage of kernels are going to pop. Right? Highest percentage, that's the maximum point. That's going to happen at the vertex. So here's what we can use that X equals negative B over 2A again, right? In this case, that's what T would equal. So T would equal negative B. So that's going to be the 2.8. So negative 2.8. And then over 2 times A, negative 1 over 250. Holy moly. All right. On your calculator, if you have that alpha y equals, this becomes really helpful here. So you can type it in as negative 2.8 and then over 2 times, and then in parentheses, negative 1 over 250. Sometimes it just makes it easier to type it all in. All right, that comes out as 350. So remember what T represents. That's the temperature. So the maximum popcorn is popping at 350 degrees Looks like Fahrenheit. And then it says also determine the percent of kernels that pop at this temperature. So they're just asking you to plug back in. So the P value at 350, we can just plug right on in. And so it'd be -1 over 250 times 350 squared plus 2.8 times 350 and then minus 394. So plug all that in, and what we end up with comes out to be 96. So what that means is at that maximum moment, that 96% of the kernels will get popped in the bag. All right. Part B, it says use the calculator and sketch the curve for when P is greater than or equal to 0, which makes sense. We don't want to see percentages, under 0. That doesn't even contextually make sense. So I'm going to type this in, -1 over 250 times x squared, and then plus 2.8x, and then minus 394. All right. To do this, if I zoom 6, it's going to give me my basic old screen. I'm not going to see a whole heck of a lot. I might not even see anything. Yeah, I don't see anything. But think about what we know right now. We know where the maximum vertex point is. It's at 350, 96. So I need to be able to see that point right there. So I'm going to change my window. So I want to be able to see as tall, as wide as 350 and as high as 96. So my Y max, percentage-wise, makes sense to go up to 100 anyways. So I'll probably leave that at 100. If I only go to 350, I'm only going to see to the middle of the parabola. So if we double that, double 350 would be like 700. Let's try that for the X max. And then don't worry about the scales and whatnot. So X max 700, Y max 100, and let's graph it. There we go. Now we can kind of see what's happening here. Right? So your sketch does not have to be perfect. Give the general idea. Mine went from 0 to 700 and 0 to 100. And then it's kind of looking like this here in the middle. All right, there we go. Next part says use the 0 command on your calculator. Determine to the nearest degree the two temperatures at which P equals 0. All right, well, if P, which is like our Y value, equals 0, that's where it's hitting the axis, because that's where the P value, this is P, this is T, right, is equal to 0. So we're looking for that value here and this value here. To do it on the calculator, we go to second and then trace and then 0. So that's what they mean by the 0 command. And it's going to ask you for a left bound, right bound, and take a guess. You're going to have to shimmy so you go just past it to the left, come on back to the right, and then take a guess. So that first one comes out at 195.08 and so on. So right about 195-ish is that first value right there, right? And then I'm going to repeat those steps. So in case I miss anybody, second, trace, 0. Then it asks for a left bound, right bound, and a guess. All right, that's the run through. So let's try it again. Second, trace, 0, and then slide all the way over. Stay to the left, hit enter, shimmy to the right, hit enter, come back. So 504.9, so that would round to 505. All right, so those are the two temperatures. So what does that mean contextually? Well, when it hits 195 degrees, the popping starts. When it hits 505 degrees, everything is burned to a crisp and the popping completely stops. There you go. All right. Part D, if a typical batch of popcorn consists of 800 kernels, how many does the Crazy Caramel Corn Company, oh my Lord, expect to pop at the optimal temperature? All right, well, we already found some things. If we come back to this graph, we found that point. That point was at 350 degrees. It popped 96% of the corn. So what that means, 96% of the 800 kernels is how much should pop. So you can do this a couple ways. You can set up a proportion to say 96 out of 100 equals what out of 800? Or we could simply say 0.96 times 800. Either way you look at it, it's going to get you the answer. So you'd either cross multiply in that first part, or we could just simply take the percentage as a decimal and then multiply it by the total number of kernels. They are equivalent. So 768. So what that means is if there is 800 kernels in there, there's 768 of them that we expect to pop. And anybody that makes, whether it's microwave popcorn or on the stove, there's always those kernels that are left over because not everything goes, right? So this is saying there would be, like 32 kernels floating around in that bag, even at the optimal temperature. All right, there's one last piece of this particular problem. When you bring it on over to the next page, it says for a batch of popcorn to be successful, the company wants at least 85% of the kernels to pop. All right, write an inequality whose solution represents all the temperatures that would ensure a successful batch. All right, so we want it to be at least 85%. So that's the p-value, all right? So if I think about this, here's the equation. I'm just copying it from the page before. That negative 1 over 250 t squared plus 2.8 t minus 394. We don't want it to equal 85. We want it to be at least 85. So we can say greater than or equal to 85% like that. Right? So when you think about it in terms of our sketch, we had our cute little parabola looking like this. And then this top was happening at 96, but they're just saying, we just want you to be at least 85. So anything here or above. So it's this little piece of the parabola that we're interested in. And how we can do this? We can do this right on the calculator. This is already in y1. Let's put that in y2. So if we take a look, oops, it's a little off the screen there. In my y2, I'm going to put 85 there. And then I can come on back to my graph so that I can see it. Let me slide this up so you can see how it matches my little sketch here. And then what I'd be looking for is what two temperatures fall between there. So I want to calculate the intersections. Between y1 and y2. So if I go to second, trace, and then intersect, oops, we can slide on over. And this is the one where you get as close as you can and keep hitting enter. So that first intersection happens at 297.5. So let's round it. We're going to say 298. So at 298 degrees is when it first starts popping at least 85%, right? It should be through that much of it. And then if we do second, trace, intersect, slide on over, hit enter, 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 at 400 and about 2 degrees. So what that means, it's gone past the peak and it's either burned some stuff up or it went so far past it that it just didn't pop as many there. All right, I'm not going to try to overthink the science of corn popping here. All right, so it's between those two temperatures that you should have at least 85% of the kernels pop here. Whew, that was a long question. All right, what I would like you guys to do, the very last thing here, is I want to do number 4, but I want to do it together with you guys in class. So all I'm asking right now is that you type this into your calculator so that we can talk about it in class. And now, in case you're like, wait, type what into my calculator? Come on down here. These have to go into the lists on your calculator. So as a little reminder, you have to go to Stat and then Edit. And I want this to go into L1, and I want that to go into L2. Get that done so that when we start class tomorrow, you are ready to go. All right, guys, thanks so much for watching. See you soon.